Greetings, my fellow retro enthusiasts. So, about 9 months ago, I did a video basically outlining, well, kind of my dream retro computer and sort of how I wanted to do it. Basically, it was just me drawing on a piece of paper. Yeah, this is test number 1. So first of all, I'm going to show you how I've got this laid out. And since everybody likes flashy lights, I thought I'd start off with viewing the flashy lights. But anyway, forgive the camera work. I'm having to put my camera on my boom arm for my mic. So yeah, my apologies right off the bat. So right about there views just about everything. Well, except this little section. So let's start with the bus that you can see clearly. Right, bus goes that way. It literally just uses, have I got a spare one? Yes I do. These things. And instead of fixed event required, instead of them being mounted to these here, above and below, I just took them all off, mounted them side by side, and made a bus. Now of course these ones are broken in the middle, so I've used some strip board and created some hard links. Yes, saves having issues with contact problems. So that's the bus. I'll go through what's on the bus in a minute. Power. Now here's the funky bit about power. That there is a lithium polymer battery. Voltage of the battery here, 3.5 volts. My apologies that it's upside down. I might actually flip this video during render. And here, underneath the massive wiring, that is a buck boost regulator. So it'll not only boost the it'll not only buck the voltage, i.e. bring it down, but it also boosts it as well. Operates down to about 2.8 volts from the lithium polymer, which is about right. So set for 5 volts, and that is the voltage readout from the output of the regulator. Charging the lithium polymer, if I can get it all the way over here, is a standard 1 amp lithium charge board, which you can just see the links here. I've just soldered it onto a micro USB port rather than a mini USB port, because these boards are the only thing that I've got that uses mini cables. Everything else uses micro or USB-C. Kind of annoying. Come on, China. Update your models to use micro USB instead of mini, please. But anyway, LCD display. You can see stuff being written to it. See if we can get this over a little bit further. There we go. Talk about that in a minute. So, what do I have here? We're going to go to the center section. So, here, Z80. This one, microcontroller. All microcontrollers that I'm going to be using, or at least those that I plan to use, are the PIC 18F46K22. It's a 40-pin microcontroller, well, at least in a DIP package, Runs at 64 MHz on the internal clock. Has a 192K of flash RAM, 4K of RAM, sorry, flash RAM, shoot me, flash storage, and 4K of RAM. It's got a load of peripherals like PWMs, analog to digital, digital to analog, comms, you name it, it's got it on board. Or at least everything that I need for the time being. Down here, right there, trying to move wires out of the way, is the RAM chip. RAM chip is 32 kilobyte. It's a Toshiba TC55257, 100 nanosecond response. It isn't the chip that I'm going to be using. It's a cheap chip that I've thrown in here just in case I blow something up. I don't want to use one of my expensive ones that runs at like 55 nanoseconds for testing. So, as you can see, wires in groups all over the place. Tried to use some sort of reasonable colour system, kinda didn't work. So let's go to the LEDs. Now I've printed off a little strip that tells me what each LED is for. The LED blocks or the bar graphs are actually in 10s, and I've been using them in 8s, just in case you're wondering. So the green, which to me is on the left, that is actually the data bus. Now the RAM chip is currently hardwired to be deselected. The Z80 data lines are hardwired to low, so it executes NOPs. The data that's on there is what's being sent to the LCD from the microcontroller, which at the moment is just test text, basically. The microcontroller isn't doing anything, it's just outputting test stuff to the LCD to make sure that bit works. Because obviously I need to see what the microcontroller is doing, where it's up to. The address bus, which is in blue, comes from the Z80. And as you can see, it just is in free mode. It's executing NOPs all the time. The red lines are the control bus. As you can see, the clock is 4 times per second, so 4 Hz. Not quite as slow as 1, but not as fast as well, this Z80 clone goes up to 6 MHz, so yeah, not quite as fast as 6 MHz. Now, one thing that I noticed as soon as I got this working is that address lines from A7 upwards flash, and yet from A6 and below they don't. And it took me ages and ages and ages to work it out, and then I realised I'm missing a control line, which is why that one there doesn't have anything next to it. I'm using static RAM and static RAM only. So the control line that I completely ignored was the refresh line. As soon as I connected that up, it then started making sense. The refresh signals are on A0 through A6. So when it does a refresh, A7 and above basically turn off. Very weird. Thank God I'm not dealing with DRAMs. Now you will also note I have A16 through A23. The Z80 only has 16 address lines, so why have I got them in? Well, I do plan on plugging in the Z180. So I extended the address lines. Now, worth pointing out, these LEDs are actually part of the pull down or pull up. So just behind them, underneath the paper strip, if I can lift it up, you can just see one of them right there. That is a resistor pack pulling up the bus lines or pulling them down. So data lines are pulled down, address lines are pulled down, control lines are pulled up. So if the bus was ever left to float, or undriven I should say, then it'll pull it down or up as needed. So right now, this is doing exactly what I want to do. It's very exciting. Even though it's doing nothing and will never do anything, this is my first home-built computer. Yay for me! Okay, that might sound completely underwhelming, but it is actually quite exciting. So, test number 1. If those of you that have viewed my first video, which is a systems design video, you will know that the microcontroller, you're set up for viewing the LEDs. That's, oh well. Move over, so you can just see the chips. The microcontroller, it's just underneath my finger here. Right. Because we're using RAM, and it's non-battery backup RAM, obviously it starts out completely blank when you switch this thing on. So the microcontroller is going to halt the processor, it's going to load the OS, or the software or whatever, and then release the Z80. So the microcontroller takes hold of the bus. So we need to tell the Z80 to release the bus and not try to do anything. So my original thought, or my original plan, was to just hold the Z80 and reset. When I read the manual, or the data sheet I should say, that's what I decided to do, which sounded like a great idea. Except when I reread it, I noticed a slight, well, the wording wasn't quite right, because it said that it released control of the data and address bus, but the control bus went to an idle state. But it wasn't quite that direct. At first glance you would have read it as it released control of all the buses. Now an idle state basically means the control bus is high. Driven high, which isn't what we want to do. We want it to release it completely, not drive it. So the only way to do that is with bus request. So the microcontroller needs to send bus request high, wait for bus acknowledge, and then it can take control of all the buses. In theory. first test, we're going to prove that. So I have, yeah, you're viewing LEDs, but I have 2 cables to do this manually. So yellow one, which is reset. So first thing I'll do is to hold the CPU in reset. There we go. As you can see, the reset's live, clock's still going. Release the reset, and everything kicks back off again. Right, that works the way it's supposed to. Next up, bus request. I'm going to do this a couple of times. Bus request, bus acknowledge. Let's do this again, and then release, it starts back off again. Bus request, bus acknowledge. That works exactly the way it's supposed to. So there we go. In order to take control of the bus, we send bus request low and wait for a low signal on the bus acknowledge. Because don't forget, these LEDs on the control side tell you the active state. So the data and address lines are active high. The control lines are active low. So first test works. So I need to do some coding for the microcontroller, but the process will be at power on, it'll reset the Z80. Like that. Hold the reset up. And then hold the bus request in. Get in there. There we go, bus request is in. Now bus acknowledge isn't coming in because the Z80 is still in reset. So then it releases the reset and the bus acknowledge then comes on. Right, when the bus acknowledge is on, then the microcontroller can take control of all buses. And then of course when it's finished doing whatever, it's going to just simply release bus request and the CPU starts off from 0 as it's supposed to. So what is it going to do? Well, quite simply, it is going to load 0 into all the RAM locations. So it's going to fill the 32 kilobyte RAM chip with zeros so that Z80 execute knobs. Simple enough. Yeah. As I mentioned before, the microcontroller, the 46K22, does not have an external data address or control bus. So all the pins are I/O pins. So we're going to be bit banging the data address and control lines. Yeah, that could get interesting. So that's going to be in test 2. Which isn't going to be now. Just in case, excuse me, just in case you were wondering, because I've got to finish wiring the RAM chip to the bus, basically the control lines, and then I've got to work out what pins I'm going to use for what on the microcontroller. Thankfully, however, definitely thankfully, that lot's arrived from China. A load more cables to do things, because this thing, I knew it's going to use a lot of cable. Wow, does it use a lot of cable? And it's going to use more. Most of it's done, thankfully. So, that'll be in the next video. Not sure how long that'll take, because I've got to look up the RAM timings and basically figure out the best way of doing it on the microcontroller. So, thank you very much for watching. I would love to know what you guys are using to compile your software. So please, I really want some suggestions for compiling Z80 software. So if you can drop those down in the comments, that would be wonderful. So ideally, it would be great if I could write software in BASIC and compile it, kind of fitting for the Z80. Quite happy to do it in assembler, but that would be awkward and long. Haven't learnt C yet. I can read little bits of C and vaguely work out what's going on. Writing C, completely different story. So let me know what you guys use, and that would be so helpful. Thank you very much, and I will talk to you again in the next video. Bye for now.